We're always told that the power of a quantum computer is all about the number of qubits. More is better, right? But it's not nearly that simple. You can't just add qubits together like you're tossing ingredients in a bowl. To get them to actually work together, to create that incredible computing power, you need a whole new language, a special kind of math. And that language is the key that unlocks everything.
And that really is the central question, isn't it? Describing one single qubit, well, that's one thing. But the second you add another one, the whole rulebook changes. So how do you combine these individual quantum systems into one single unified whole? The answer, it turns out, is not as simple as 1 + 1 = 2. Not even close.
So, here's how we're going to break this down. First, we'll really dig into this multi-qubit problem. Then, we'll introduce the special math that actually solves it. We'll see how that math leads to entanglement, which is really the secret sauce of quantum mechanics. From there, we'll look at the huge challenge this power creates, and then finally, we'll tie it all together and see why this is so critical for the future of computing.
Okay, let's start with the problem itself. Because in the quantum world, scaling up isn't like, just adding more RAM to your laptop. It's more like you're adding a whole new dimension to reality. You're not just getting more of the same thing, you are creating a system that is fundamentally different and just unbelievably more complex.
Here's the heart of it. We need one single, consistent way to describe all these individual qubits as if they were one coherent thing. We can't just look at qubit A over here and then qubit B over there separately. We have to be able to talk about the state of qubit A and qubit B together as a single entity. And for that, we need a new tool in our mathematical toolbox.
And that tool, the hero of our story today, has a name: the tensor product. This is the mathematical operation that lets us speak the language of multiple qubits. It's the whole key.
So what in the world is this thing? Well, the tensor product, you see it as that little circle with a cross in it, is our way of combining the individual worlds of each qubit. Think about it like this. If each qubit lives in its own little two-dimensional world of possibilities, the tensor product doesn't just put those two worlds next to each other. No, it multiplies them together to create a brand new shared four-dimensional world for the combined system to live in.
Okay, let's make this real for a second. Let's say we've got one qubit in the state 0, and a second qubit over here is in the state 1. To describe the combined two-qubit system, we use that tensor product. We write it as the state 0 times tensor the state 1, and that gives us a brand new two-qubit state that we just call ket 01. This new state, it lives in a much larger mathematical space than either of the original qubits did on their own.
But this is where it gets really, really cool. This new math doesn't just give us one way to combine qubits, it actually creates two fundamentally different kinds of systems. And one of them is where all the quantum magic happens.
So on one hand, you've got what are called separable states. You can think of these as pretty simple combinations. Like the state 00, it's easy to see that's just a qubit in state 0 combined with another one. They're independent. But then you have entangled states. These are special, weird states that you simply cannot break down or factor back into their individual parts. The qubits are now fundamentally linked.
And this is the absolute crucial point. With entangled states, the system becomes more than just the sum of its parts. The individual qubits almost lose their separate identities. Their fates are now completely intertwined, which means if you measure one qubit, you instantly affect the other, even if they're on opposite sides of the galaxy. This is that spooky action at a distance that famously freaked out Einstein.
So this entanglement thing gives us this incredible, almost unbelievable power. But that power comes with a price. A steep and, frankly, a monumental price. And it's called exponential scaling.
So when we combine just two qubits, the number of possibilities we have to keep track of, what we call the dimensions of the system, jumps from 2 to 4. All of a sudden, we're working in a four-dimensional world.
Add just one more qubit, and it doubles again. Now we're at 8 dimensions.
And you can see the pattern here, right? With every single qubit we add, we double the complexity of the system. This is exponential growth in its purest form, and it gets out of hand fast. By the time you get to just 300 qubits, you would need more numbers to describe that system than there are atoms in the entire known universe. Just think about that.
And this is the great paradox of quantum computing. The very thing that makes these systems so powerful, this explosive, exponential growth in the information they can hold, is exactly why your laptop or even the world's most powerful supercomputer just can't simulate them. They literally run out of memory trying to keep track of a reality with that many dimensions.
Okay, let's tie all this together. Why is getting our heads around this complicated math so absolutely fundamental to the future of quantum computing?
So, it really all comes down to this. The tensor product is the special language we use to combine qubits. It's the thing that makes entanglement possible, and entanglement is the engine of quantum power. But it's a double-edged sword, because it's also what causes the system's complexity to just explode. Mastering this delicate dance between incredible power and unimaginable complexity, well, that's the fundamental challenge for anyone trying to build our quantum future.
And that leaves us with a really fascinating question to think about. We've established that the tensor product creates these systems that are just way too complex to simulate directly. So the new frontier of this field is asking, are there smarter mathematical tools like these tensor networks that can help us cut through all that complexity? Could they be the key to actually managing, simulating, and ultimately building the powerful quantum computers we're all working towards? That is the challenge that lies ahead.